For today's quiz, we're going to talk about two metal plates. Notice that I'm grabbing them by a plastic knob. But either way, this is a metal plate and this is another metal plate. Let's say that I have these plates separated by some distance. I'm going to put positive charges on this plate, negative charges on this plate. What we'd like to know is what would happen to the voltage if I took the plates and then physically separated them a greater distance. This is what the quiz looks like. I'll hold it up now. As always, please write down as much as you can about your thoughts. Pictures help. This is a really nice quiz for teachers, even if they don't have the equipment that's sophisticated enough to be able to measure the voltage. Students can still engage in dialogic discourse to figure out what their thoughts are and how confident they are about their answers. So let's start going over some typical student responses. The first that we normally get is we end up having the idea that as you separate these plates, the voltage would go down. They're not really sure exactly why. Others will think, well, I don't even understand the voltage, so I'm not sure how that relates to this problem. But there are some that will say, no, I think the voltage actually increases as I pull these plates across. We're going to go over a couple of these methods for figuring out which of these answers are correct. In order to explain what's happening here, let's go ahead and draw these out. This might take a minute. I'm now going to end up putting some charges on each plate. I'll put 4 positives on the right and 4 negatives on the left. Doesn't matter really how you put them, but regardless, students will often instantly go to their parallel plate capacitor formula, which is just going to be parallel plate capacitors equal to epsilon naught, and how big the area is, divided by the distance. Now, just to show that this is an area, maybe I'll put an area on the diagram here. So that area and that area. The area doesn't change. So if they're close together or far apart, so let me draw them far apart now. You'll notice that I still have the same areas I had before, and epsilon naught doesn't change either. So what we can say from this formula is we can go to proportionalities. We can say if A doesn't really change, and if our epsilon naught doesn't change, we can say capacitance parallel is proportional to 1 over the distance. We can clearly see that's a bigger distance and that's a smaller distance. From there, students might say, oh, we also understand what capacitance is. Capacitance is our charge per voltage, whatever our voltage happens to be. We're looking for voltage here. So our charge, you can see I still have the same number of charges as I had before. So that's not going to change. So I could also say capacitance is proportional to 1 all over the voltage. Right away we could see if capacitance is proportional to 1 over D and capacitance is proportional to 1 over V, we think they're going to be proportional to one another. Let's write this out a little bit. If capacitance is proportional to 1 over D and capacitance is proportional to 1 all over V, we could say, therefore, 1 over D is proportional to 1 all over our voltage. I can flip both sides, and I could say our distance is proportional to our voltage, or as the distance increases, our voltage increases. So that's where students say the voltage would increase. This is our first method that we often see students working through. And this is a really nice way to tell if your students understand what's going on with not only parallel plate capacitors, but do they actually understand how that relates to capacitance in general. Let's put method 1 right here. So that's method 1. A second method that students often come up with is thinking about in terms of energy. If I had 2 plates here and then I had to raise one up higher. Often we'll use this notion that I had to do work in order to raise them, which is nearly the same as pulling them apart. I'm going to draw these vertical. They're the same size plates, and maybe I'll put my positives on bottom here, and I'll put my negatives up top. And you'll notice the charge hasn't changed. Maybe I'll put a little line for each one of these capacitors. Up and down. This would show a small distance, where this would be a large distance. Students will often say, well, I do understand potential energy from working in mechanics, and that potential energy is related to our mass, our gravity, and our height. They can use an analogous form for potential energy, stating that instead of masses, we'll end up using charges. Instead of a gravitational field, we can use an electric field. And instead of height, we can end up using our distance. Now, the charge stays the same, even if we raise these. Our electric field, students know, and the electric field is proportional to the electric flux. In other words, I could say I have equal number of field lines on each of these. So my electric field doesn't change. In other words, our potential energy is proportional, if these two are not really influencing, the distance. We can also say, and voltage, the very definition of voltage is potential energy per charge. Again, the charge is not changing, so I could say my voltage is therefore proportional to my potential energy. So we could say, therefore, our voltage is proportional to our distance, which is proportional to our potential energy. Right away, they've already solved it. As the voltage goes up, you would have expected the distance to have gone up. We might want to put it the other way, just like we did over here. As the distance increases, the voltage increases. We'll call this method 2. So far we have 2 really nice methods. If your students are thinking through the problems like this, They're doing a great job. I'm going to move the camera over a little bit. We'll see if we can squeeze this last one in. Let's just use the same diagrams that we have before. Some of them will say, well, a third method simply says, well, why don't we just use our voltage is equal to the electric field times the distance. And if they start with this, life is a lot easier. Because here, as we said, the electric field, as we can see, doesn't really change here. So we could say our voltage is simply proportional to our distance. As the distance increases, the voltage increases. This is how you know that your students are really engaging and thinking through the problem and that they understand capacitance, voltage, and so on. So that's your quiz for today.